Okay, so welcome back. I think today we're going to step up a notch in terms of the difficulty level. I want to remind you that it's important both for you and for me that you ask questions. You can ask different types of questions, like on notations, on some argument you didn't understand, or some questions about the general context, and so on. So I would like to remind you to try to ask questions. This will turn the lecture into more into the direction of a dialogue, which is I think is better. So last time we defined the notion of a group. So a group G, group is a set G plus a binary operation, multiplication, such that for any x, y, and g, for any x, y, and z in G, we have associativity, that is x, y, z is equal to x, y, z. For any x in G, or maybe there exists a specified element E, which we call the neutral element, such that for any x in G, Ex equals to Xe equals to x, and for any x in G, there exists an element x minus 1 in G, such that x times x minus 1 is equal to E, but also on the other side, x minus 1 times x is also equal to E. Now, from the axioms, it actually follow that the unit element, or the neutral element E, is unique. The neutral element is unique. What do I mean by that? It means that if there would be another candidate for a unit element, so if E prime in G is such that for any x in G, E prime x equals x, and also x times E prime is also equal to x, then E prime must be equal to E. Well, how do you see it? I mean, E prime E, it must be equal to E because E prime is a neutral element. But it also must be equal to E prime because E is a neutral element. So you get this small fact. You cannot have two neutral elements. I mean, similarly, the inverse of X is also unique. And what I mean by that, if well, if for any X in G, there would exist let's call it X minus 1 prime in G, such that X times X minus 1 prime is equal to E, and also from the other side, then X minus 1 prime would be equal to X minus 1. This I leave as an exercise. And the third remark is that it's enough if we, so here in the inverse axiom, we required that the inverse would be a right inverse and also a left inverse. But it is in fact enough to require that you have for any X you have let's say a left inverse. So if let me just say it briefly. You can find the details in the notes. It is enough to ask for a left or right inverse instead of two-sided. So this you can try to do the exercise to do this as an exercise. It is important to do these small exercises because you get comfortable with the axioms. And of course, you could, since you have these remarks tell you that you could have formulated the axioms slightly different, and you would get the same notion. But the way it is written here above is the standard way to define it. Okay. Now, what we also had last time is we took the unit circle within the complex numbers. And I remind you, the complex numbers I represent, it is all the z such that the z is equal to r cosinus theta plus I sinus theta. For some theta in the interval 0 up to 2 pi. And so this is the complex numbers, right? This is what is called the polar representation. So if you have a complex number here we denote the real axis and the imaginary axis, right? So z is also x plus iy. Then this is the radius. Of course, this is y, and this is x. And here you have theta, which is the angle that z creates with the positive direction of the x-axis or the real axis. So under this representation, I can look at the circle as simply the collection of all complex numbers, such that the radius, this we call, we denote the radius by absolute value. So the circle is simply the complex numbers whose absolute value is 1. And of course, we have a natural operation on the circle, because if you take z and z prime, you can simply add the two angles, right? And you get something like this. This would be z multiplied by z prime. So here, multiplied really means that I simply add the two angles. Now, let's consider the equation x to the n minus 1 equal to 0. And I define mu n of C is the solution set over the complex numbers to this polynomial xn minus 1. So it's all the zeros of this polynomial. This is called nth roots of unity. So, for example, if you take I, you know that I square is minus 1. So I to the 4 is going to be 1, and therefore I to the, well, I is going to be an element in mu 4 of C. Now, how can we, so we fix an n, and we would like to understand the entire collection mu n of C. Well, you can see that since this is a complex number in mu n of C, since it needs to satisfy that z to the n is equal to 1, it follows that the absolute value of z is 1, because when I multiply complex numbers, I multiply the radius. So So the radius must be 1. So it means that it is on the unit circle. And moreover, well, I can heuristically guess what are the possible solutions to this equation by the geometry of the unit circle. That is, well, of course, this is 1, right? One is always going to be a solution to the equation x to the n minus 1 equal to 0. So this is always in mu n. But then, I mean, if I take an angle which is 2 pi over n, then if this is z, let's say z is equal to cosinus 2 pi over n plus I sinus 2 pi over n, then when I do z to the n, it's simply doing a addition of the angle of z n times. So I get cosinus 2 pi plus I sinus 2 pi, which is by properties of sine and cosine, it's simply 0 plus, sorry, 1 plus 0I, which is 1. Okay, so here this is always a solution to this equation. This is an nth root of unity, and in fact, I can also do a similar thing by taking here z prime, for example, to be 2 pi times 2 divided by n. Because maybe I should say this angle. I could also take 2 pi times 2 divided by n. That's also when I raise z prime to the nth power, I also get a multiple of 2 pi. So I will also get the unit element 1. So also z prime to the n is equal to 1. And similarly, so what is happening here, I can divide, let's say n equals to 3. I can divide the circle into 3 equal parts. So let's say yeah. So I have my so I want this would be, of course, 120 I guess it would be something like this. My drawing skills are not that good, as you can see, but the important thing is that you divide the circle into three equal parts, and then so you have Z1 is simply equal to 1. Z2 is whatever this is. I mean, it corresponds to theta equal 120 degrees. And Z3 is going to correspond to 240 degrees. Okay, and so this if you write it in radians, then this would be 2 pi times 2 divided, sorry, 2 pi divided by 3, and this would be 2 pi times 2 divided by 3. Okay, now this kind of object, I mean, it is a group as well, because so note mu n of C is a group under the operation under multiplication of complex numbers, and the size of mu n is simply n. There are you cannot have more than n solutions to a polynomial of degree n. Okay, because you can write. I mean, so in fact, whenever Z0 is a solution to the polynomial x to the n minus 1, for example, then you can write x to the n minus 1 equals x minus Z0 times some polynomial g such that g the degree of gx is strictly smaller than n. So if I know that there could be at most n solutions to this equation, and heuristically I found all the n solution, I mean I found n solutions, it means I described it completely. And so I have the number of elements in the set of n roots of unity is n. And the operation of multiplying complex numbers is giving me a group, because I mean you can look at it in this description. Of course, if you multiply two things in this triangle, you simply add the two angles. So either you add 0 to 120, or you add the 120 to 240. You get still again an element in this, or you get again an nth roots of unity. Any questions? Come on, guys. I'm sure something here might have not been completely clear.
Hi.
Yeah.
Yeah, I have one question. So I kind of missed out on how you got z1 equals to 1 on the n equals to 3 diagram. Could you repeat on that?
Z1 equals to 1?
Yeah.
Oh, okay. So, I mean, this is I mean, you could say this is a 2 pi times. So I'm looking for the solutions of the equation x to the n minus 1 equals to 0. So one is an element in the complex numbers, right? I mean, you can write 1 plus 0i.
Yeah.
Okay. And of course, when you do 1 to the n minus 1, you get 0.
Right. Okay.
Okay. So again, the enumeration here, I called it Z1. Sometimes you start enumerating by 0, because Z1 corresponds to the angle of Z1 with the axis real is 0. So in polar coordinates, the angle of Z1 this corresponds to theta equal to 0.
Okay, got it. Yeah, thanks.
Okay, and in fact, Z1 will always be so 1 is in mu n of C for any n, right? So this is not a, I mean, it's not a special property of the n equals 3. For any n, you raise 1 to the nth power, you get 1. And this is the unit element in mu n. So this is the unit. Okay. Other questions? All right. So what is happening here? We have this circle. Which is a group by multiplication of complex numbers, and within this group, I have another subset. Let's say n is equal to 3. And this subset is also a group under the same operation. And it also has the same neutral element, right? Because here, 1 is also the neutral element of the group S1. So this calls for a new definition. Let G be a group a subset H in G is called a subgroup if, well, we need a few conditions. First, we need that the unit element or the neutral element will be in the candidate for a subgroup. 2, we need that the subgroup is closed under the binary operation of G, that is, for any x and y in H, x times y, the same operation as in G, the only one that we are given, is also an element in H. And 3, for any x in H, the inverse of x is also in H. Who can tell me? So I claimed that mu3 in this example of C is a subgroup. Should say we denote age smaller or equal to G. This is our notation for a subgroup. And I claim what we discussed just a minute ago is that we have a subgroup of S1. So here, for example, we enumerate this as Z1, Z2, Z3. Who can tell me what is the inverse of Z2? What is Z2 to the minus 1?
That's 3.
Okay, so let's check. Let's say I do Z2 times Z3. Then Z2 is like, it's 120 degrees. And Z3 is 240 degrees. So indeed, when I do Z2 times Z3, I get a 360 degrees, which is 0. So I mean 0 degrees. So this corresponds to 1. So we can say that Z2 minus 1 is Z3. Okay. Now let's talk more about subgroups. I mean, this nth roots of unity is a nice example that we will revisit, because, well, okay, we'll leave it for later. But for subgroups, we have many examples actually. This is a very very common object you run into. So the first example, I take G to be the integers, with the neutral element being 0 and the operation being plus. And I take H to be what I denote as NZ. NZ is the set of all numbers of integers of the form n times a, or a is an integer. So for example, n equals 2 it's all the even numbers. Then age is indeed a subgroup of G. Now, what if I take G the same as above, so G is equal to Z. Age is equal to all the odd numbers. Is this a group? A subgroup, I mean.
When you add odd numbers, you get an even number.
Exactly. So it is not closed under the binary operation. So this axiom is not satisfied, but there is also another axiom that is not satisfied. What is it?
There is no neutral element.
Exactly, because the odd numbers do not contain 0, and 0 is the neutral element. So also this axiom is not satisfied. Okay, so this is a non-example, maybe slightly more interesting. You take, let's say, Z mod 10, which I remind you is all the numbers up to 9, I mean 0 up to 9, with a modulo 10 addition. And now I look at the set 0 and 5. This is a set of 2 elements. It is contained in Z mod 10. I call this H. This is H and this is G. And I claim that H is a subgroup. Well, what do I need to check? The unit, so the first axiom is the unit element or the neutral element. Indeed, 0 is in H. Then I need to check that this subset is closed under the binary operation. Well, if I do 0 plus 5, I get 5. If I do 5 plus 5, I get 0. So I mean, I'm always closed under the binary operation of modulo 10. And the inverse of any element is also in the group, because the inverse of 5 is simply 5 itself. Okay, but note that if I take the subset 0, 4, for example, this is not a subgroup. It is a subset, but it's not a subgroup, because I add for example, I add 4 to itself, I get 8, which is not an element in this set 0, 4. Okay, another example. You take the complex numbers, but you remove 0. And you take the operation is multiplication, and the unit element is 1. Then I claim that S1 is a subgroup of these complex numbers. I mean, what is called, this is denoted as C and cross above. The multiplicative group of the complex numbers. And it follows that we have like a sequence of subgroups. So we have mu n of C, is a subgroup of S1, which in turn is a subgroup of C star. And of course, well, I mean, you can check it, but a subgroup of a subgroup is going to be a subgroup as well. I mean, so mu n of C is in fact a subgroup also of the multiplicative group of the complex numbers. And a exercise. You take two groups, G and H, and you look at the Cartesian product. Now here, inside the Cartesian product, you can look at a subset of the form G times the neutral element of H. This is simply a notation to say it's the set of all pairs of the form X, comma EH, where X is in H. Sorry, X is in G. Then G is going to, G times EH is going to be a subgroup of G times H. Okay, and similarly, EG times H is going to be a subgroup of G times H. Now, of course, you can really think of EG times H as it is like a copy of H. I mean, we didn't do really anything, and this is like a copy of G. Okay, we will get back to this this issue more precisely later. So let G be a group, and H a subgroup. The H coset for some X in G is something I denote as X times H. This is the set of all products X H such that H is in H. So you see, I am using this binary operation of the group to in an abused notation. I mean, now I use the binary operation to have an element on one side and a set, or in fact here it's a subgroup on the other side. But I think it's intuitive enough that you can get used to it, and in any way that's the conventional way to write it. So this is the coset defined by an element in G. Note, for example, E times H is simply equal to H, because what is E times H? I mean, it's all the products of the form E times age is in age, which is simply all the age such that age is in age, which is age. So that's the first thing. Second, if I have alpha in X age, say alpha is equal to X times age for age in age. Then this lowercase h is unique. That is, if also alpha is equal to X times h prime, then, well, I have xh prime equals to xh. But I can multiply this equation by x minus 1 on the left, and I get that h is equal to h prime. Okay, so here's a question. Let's say age is finite. It could be like this a group of n roots of unity. What is the size of xh? Anybody? I mean, let's say age has 6 elements. What is the size of xh?
It's the same.
It's the same, right? Because
It's
every element has a unique representation. So, I mean, all I did here is I shifted age by the element x, but this shift is like, I mean, it's like all the x ages, each of them, I mean, every two different, I mean, if age is different than h prime, then you get x age is different than xh prime. So it's exactly the size of age. Okay, example. Now, I take g equals to the integers, and age is equal to nz, which is like integers that are multiples of n, right? This is like na such that a is in z. And remember, the operation in z in the integers is plus, right? So I will write the cosets. So for x in g, I will write the cosets xg, sorry, xh, I will write x plus h, right? Because plus is my binary operation. So x plus h is going to be the set of all expressions of the form x plus h, such that h is in h. So, Okay, so I have, for example, the coset 1 plus nz. But the coset 1 plus nz is in fact equal to the coset n plus 1 plus nz. Because this, when I do, I mean, if you do, for example, you open this up a bit, this is all the n plus 1 plus na, such that a is in z. But if a is allowed to be in z, then I can unite these two components. So I get that it's the same as like saying 1 plus na. If you want, it's 1 plus I mean n times a plus 1. A is in z, but this is really the same as taking simply 1 plus a is in z. So so these two things are equal, and I can further say that this is like, it's also equal to 2n plus 1 plus nz. And so on. It is also going to be equal as a set to minus n plus 1 plus nz. Okay? So in other words, you can check that x plus nz is equal to y plus nz if and only if x is equal to y modulo n. Right? I mean, another example, you can take 0 plus nz. This is going to be equal, well, to n plus nz, and also to 2n plus nz, and so on. Now, consider the set all cosets of nz where x is in z. This is a set of sets, right? We talked about it in the first lecture. Remember that when we describe a set, the order doesn't matter. The order of the elements doesn't matter, and we also remove repetitions. And here is a key example where you need to remove repetitions. So after removing repetitions, we can write that the set of all cosets, one way to describe it, it's not the only way. I can write, well, I have 0 plus nz, then I have 1 plus nz, and so on, up to n minus 1 plus nz. And then n plus nz is already equal to 0 plus nz. So I don't write it. But of course, I could have written it differently, like this is also equal. For example, I replace the first element by 2n plus nz, and then I leave the rest of the elements the same. 1 plus nz up to n minus 1 plus nz. Okay, but this purple way to write the set of cosets is kind of canonical, right? We have all the elements 0 up to n minus 1. This is kind of a familiar pattern for us. Any questions about what we did? Okay, so I suggest we take a 10 minutes break. See you back here in 10 past 11.
Okay, yeah.
Okay.
Okay, so I saw somebody asked in the chat to give again an overview of where we are going. Well, first, I want to say it's hard for me to look at the chat while I'm talking. So please speak up. But this one I saw, I can say that the plan of next steps. Well, we have quite a lot to cover before we can get to elliptic curves with the proper background. So we will need to talk about more about groups. And specifically Cauchy theorem and the isomorphism theorem and cyclic groups. Then we will need to talk about fields. Here, of course, you know the main example, this prime field, but in fact, there are also fields of the form fp to the n. And to prove, I mean, basically to classify all finite fields, this requires quite a lot of work. I mean, you need to look at polynomials over fields, and well, you have a theory of classifying all the finite fields. Then we will need to talk about the algebraic closure. The algebraic closure of a field. We only do the finite field version, so it's a bit easier, but still it requires some effort. And after we did all that, we can get into elliptic curves. So I know that Mitzo wrote in his notification that we might be able to get to the material needed for pairing, but this is, I think, this is too ambitious. I mean, in a few months, I think we can get to elliptic curves. I'm not sure if it's going to be a 2 months or 3 months, but something like that. But even after we get to elliptic curves, there is a lot to cover until we get to pairings. So this is because we are doing everything with almost full proofs. You could do it differently by using things as black box, but that's a different approach than what we're taking. Yeah, so somebody asked if we can skip to polynomial rings, right? I think it's not wise unless, I mean, all of you tell me that it's this material is you're completely fluent with, and I really kind of doubt it, because if you didn't study like proper course in field theory, then at least this material with the algebraic closure especially, you will not be completely fluent or familiar with, and it is essential to things we do with elliptic curves. So that's, but I'm open to get your to get your input. Maybe later after the talk, we have the Discord chat for that. Okay. So before the break, we talked about this example of cosets, and you can see that if I take the union of all cosets, X is in Z, I get Z itself, right? I mean, every element is an element in some coset. I mean, these cosets simply cover everything. And this is not a coincidence. This is in fact a general phenomena. So proposition for group G and a subgroup H, the set of cosets XH, X in G, form a partition of G i.e., 1, the union of all cosets is G itself, and 2, if you take two cosets that are not equal, and of course, two cosets could be equal, as we saw in this previous example, but if they are not equal, then they must be what is called disjoint. It means that the intersection is the empty set. Okay, so the picture is like, well, I have maybe x1 age, x2 age, x3 age. Maybe x3 age is equal to x4 age. That's also okay. But they don't have any intersection if they're not. I mean, two cosets do not have any element in their intersection unless they are equal. And the union of all cosets is the group G. Okay, so why first? Why the union of all x age is G? Well, if x is in G, then x in particular, x is equal to x times e, and e is in age, so x must be an element in x age. So since this is true for any element x, 1 is proven. Now, suppose you have two cosets and you have an element. Then there exists H and H prime in H, such that alpha on one hand is equal to xh, and on the other hand is equal to xh prime. Sorry, to yh prime. Any question? There. Okay, so if I have an element that is in the intersection of x age and y age, then it can be expressed in two ways. First as x times age, and second as y times age. But remember that I can take inverses in a subgroup age. So for example, I can multiply this equation by the inverse of age on the right, and I get that x is y h prime h minus 1. So x is in yh because it can be expressed as a y times some element in h. And also y is going to be equal to x h h prime minus 1. So y belongs to xh, because this element is an element in H. Well, so but
I have a
if
question.
yes,
So my question is, so I think you just said that the union of all cosets is equal to the group, right?
yes,
But the coset alone, it does not build a group or a subgroup, right?
yeah,
Or
a coset alone is, in fact, it's not even a subgroup.
yeah, that was my
Typically,
question. Yeah, okay.
but the exception is the coset EH is equal to H, which is a subgroup.
Mhm.
But the rest of them, they are not subgroups, because, well, you will see. I will give an example after the proof.
Okay,
Okay.
thanks.
Okay, so we have x belongs to yh, but if x belongs to yh, let's call it star, and this I call double star. I mean, from star, I can deduce that xh entirely is contained in yh, because I mean, I take an element xh, then it is of the form y times, I mean, x is of the form y times h prime, and this times h, then it is, but now I use associativity. This is like y h prime h, which is an element in h. So this belongs to yh. And double star similarly would imply that the whole coset yh is included in xh. So both of these things imply that xh is equal to yh. And this is a method that we will repeat. I mean, to show, it's like to show the two numbers are equal. You show that the first is smaller or equal than the second, and the second is smaller or equal to the first. And the analog in sets is to show the inclusion of both sides. Okay, so what we deduced? So of course, if the two cosets are not equal, I mean, or if they have even one element, then they must be equal. So it means that if they are not equal, they don't have any common element. This finished the proofs. Okay. Now a lemma for H subgroup of G as above. Now I want a criteria for when two cosets are equal. We saw that in this example, the two cosets, for example, 1 plus nz was equal to n plus 1 plus nz. But what is the general criteria? This example of integers modulo n is kind of maybe too simplistic. We don't know. So the criteria is the following lemma: two cosets are equal if and only if x minus 1 y is an element in H. And of course, the roles of x and y here are symmetric, so you could equally well write y minus 1 x is an element in H. Okay, so this, if and only if this blue symbol, it means that I need to prove both directions. I need to prove that if the two cosets are equal, then x minus 1 y is in H. And conversely, if x minus 1 y is in H, then the two cosets are equal. So let us start. So suppose xh is equal to yh. Then, since y is in yh, which is equal to xh, so there exists some h in H such that y is equal to xh. But then I can multiply all this equation by x minus 1, and I get that x minus 1 y is H, which is an element in H. So this is the easy direction. And conversely, if x minus 1 y is in H, we write x minus 1 y is equal to some H. Then I multiply all this equation by x, and I get y is equal to xh, i.e. y is an element in xh, and as we saw, it really means that the whole yh is included in xh, because an element in yh would be so yh, and y is some xh. So let's say this is yh prime. This is going to be xh h prime, and this is in xh. And but also, so if I have this, I can write, let's say, x minus 1 is equal to h y minus 1. You know what? There is a simpler way to do it. Now I want to show that x is an element in yh. But x is equal to y minus 1. Let's say y minus 1 h. Sorry, x. Right, this is I have this is the same as like saying x is equal to y minus 1 h. So I write it as yeah, so okay, so in fact we don't by what we saw there is a simpler argument. Then so I have then what we saw. I mean, y of course is an element in y age, and y is also an element in x age, and we saw that two cosets are either equal or disjoint. So since in this case they have a common element, they must be equal. Okay, I'm sorry for the unnecessary complication. Now, suppose H is a subgroup of G, and X and Y in G are such that X age is different than Y age. Define a function let's call it f from X age to Y age where f I need to tell you what it does on X age. I mean, every element alpha here, it can be uniquely written as some x times age. This age is unique. So I can define the function on this expression x age. And what I do, I send it to y age. Very, very intuitive. Then, well, and first, you can see that f is surjective. Because if you give me some element, beta in y age, then this beta is of the form y age, and so f of x age is going to be y age. If you write alpha equals to x age, then f of alpha is equal to beta. But also f is injective, if you have two elements, alpha and alpha prime, in xh, so say alpha is equal to xh, and alpha prime is equal to xh prime. Then, of course, age must be, so if I have two different elements, alpha and alpha prime, then age must be different than h prime, right? Because if they would be equal, I could multiply by x minus 1 and get that age would be then equal to h prime. So y age must be different. I mean, I have now f of x age, which I know by definition is y age, and I have f of xh prime. This is like, maybe we do another step. So I have f of alpha. This is by definition of alpha, this is f of xh. And by definition of f, this is this is yh. And on the other hand, I have f of alpha prime, which by definition of alpha prime is xh, f of xh prime. And by definition of f, it's yh prime. And of course, yh cannot be equal to yh prime because if they were equal, I could multiply by y minus 1 on the left, and I get age equal to h prime. And that's a contradiction. I mean, we assumed that alpha is different than alpha prime, and this means that h is different than h prime. So this is all to say that f is injective as well. And what we get is a bijective map from xh to yh. E.g., if h is finite, all the cosets are of equal size. The number of elements in xh is going to be the same as the number of elements in yh for any x and y. But if this is true for any x and y, this is also true for x being the unit element. So it's like it's going to be equal to the number of elements in E times H, which is simply the number of elements in H. So in fact, we can revisit the picture, and if this is G, and so if G is finite, then I get like a partition of G. Let's say this is x1h, this is x2h, x3h, maybe x3h is equal to x4h, and so on. But the size of the slices is exactly the same. Okay, and there is an immediate corollary for this. This is called Lagrange theorem. If G is finite, and H is a subgroup of G. So of course, H then must be finite. Then the number of elements in H must divide the number of elements in G. And the proof is, it's basically what we saw. I mean, we can write G as the union of all cosets. Here in the union, there is repetition somehow, because it could be right that xh is equal to yh. This, we saw that this happens if and only if y minus 1x is in H. But regardless of whether there is repetition or not, these sets in purple are of equal size. So I get that the number of elements in G is some C times the number of elements in H, where C is the number of distinct cosets xh. Any questions? We did quite a bit by now, so this would be a good opportunity.
So does that mean that groups with a number of elements which are prime, that those groups don't have a subgroup?
Exactly. Apart from, I mean, you always have the trivial. So if G is a group, then first of all, G in itself is always a subgroup, and also the set with only the unit element is also a subgroup. These are called trivial subgroups. So what you say is exactly right. I mean, if G is of prime order, and this is the reason that we use groups of prime order in cryptography, then there is no non-trivial subgroup for G, and so this has implication in the cryptographic primitives that we construct. Other questions? Okay. I guess maybe we let's call it a definition. Suppose G and H is above. They don't need to be not necessarily finite. And for two elements, x, y in G, I have the coset xh, and I have the coset yh. And I can do a binary operation by saying that the multiplication of these two cosets is defined to be x, y, h. And I can also do inverse. I take this coset xh, and you want to know what is the inverse. I tell you what is the inverse is like x minus 1 h. It's another coset. Okay, so notation. We call you have a subgroup H of G, and the set of all cosets. I'm not sure if I said it before, but I denote it as this G divided by H. This is like the set of all xh, x in G. I can tell you a bit more about the intuition for this notation, but for now, just think of it as like in the example we had of the coset H is equal to n z, then the set of all cosets was like 0 plus nz up to n minus 1 plus nz, and this really this really resembles the mod n, I mean the integers modulo n. So it is like I took integers, and if I divided by the subgroup of all integers that are multiple of n, I got something that is similar to integers modulo n. So this is maybe a heuristic justification for this notation. And the main issue of this this is called the quotient. Of G by H. And this definition is telling you something. In fact, I would like to say, so this definition is like defining a binary operation on the set G mod H. And of course, we want that this binary operation will be a group. It is it looks like this definitely, but there is an essential condition that we need to add in order for this to happen, and this is the proposition: if G is a billion, that is xy is equal to yx for any xy, then star induces a group structure on G mod H. Okay? And now, how do you prove it? Well, first, and this is a repeated principle in definitely in quotients, but we will run into it in I mean later on as well. I gave you a definition, and maybe you're not that experienced, but nobody told you that what I defined is indeed well defined. Why? Because I took the representatives X and Y and I multiplied them. But it could be so. So need to check that the binary operation on G mod H is well defined. Why? I mean, you gave me X age and Y age. And I told you, okay, I can multiply. I do X age, sorry, XY times H. But suppose you now tell me, okay, but instead of X age, I give you X prime age. And X prime age is equal to X age, but X is not equal to X prime. And also, I give you instead of Y prime, Y prime age. And these two cosets, Y age and Y prime age, are equal, but Y and Y prime are not necessarily equal. Then I get a coset like this, and I need to show that these two cosets are equal. I mean, this is what it means to be well defined. I mean, it means that it does not depend on the representative of the coset that I chose. So if X age is equal to X prime age, then X minus 1 X prime belongs to H. And if I know that Y age is equal to Y prime age, then I know that Y minus 1 Y prime also belongs to H. And now to show that XY H is equal to X prime Y prime H, it is enough equivalent enough to show that XY minus 1 times X prime Y prime is an element in H. But XY minus 1, this is in any group, is going to be equal to y minus 1, x minus 1. So what we need to show is that y minus 1, x minus 1, x prime, y prime is an element in H. And what I have is the two blue boxes that I started with. I mean, I started with two different representations of the coset, and they gave me the blue boxes. But now I use the fact that G is a billion. If G is a billion, then I can write it as I can just order all these symbols in whatever order I choose. So I choose x minus 1 x prime times y minus 1 y prime. The first blue box tells me that this is an element in H. The second blue box tells me that this is an element in H. So all in all, the entire product must be an element in H, because H is a subgroup and it is closed under products. So okay, so this is all to say that the definition is well defined. But now the rest of the axioms of a group, they follow immediately. So associativity unitary or unitarity and existence of inverse these axioms in G mod H follow from these properties in G, because, for example, associativity xh multiplied by yh, and then you multiply the result by some zh. Well, now that we have a well-defined binary operation, we do, this is xyh multiplied by zh, which is xyzh. But since the binary operation on the elements x, y, and z is associative, it is also equal to x times yz h. And if you open it from the other direction, what you get is like that this is simply xh multiplied by yh zh. So you get associativity of multiplication of cosets. Unitarity is in the same way. I mean, of course, xh times eh by definition is x times eh, so it is simply xh, and the existence of inverse, well, x xh times x minus 1h is going to be equal to x minus 1h, which is simply EH. Okay, so this finishes the proof. We get under the condition that G is abelian, this collection G mod H is a group. And let me give like a quick example. I mean, we have a running example, remember. You take G to be equal to the integers. That's an abelian group, so we are okay. And H is multiples of n. Then G mod H, we saw that as a set, it is like 0 plus nz up to n minus 1 plus nz. But now the last proposition tells us that this thing has a group structure. And the group structure is you take a coset 0, x plus nz, and you want to add it to a coset y plus nz. Well, then you just do x plus y in the ambient group G, and you add it to the coset nz. But we saw that x plus y nz is the same as x plus y mod n. Plus nz, right? Two cosets in this running example, two cosets are equal if and only if their representatives are equal up to a modulo n. So in fact, what is happening here is that we have, it's like a funny way we have, instead of the numbers 0 up to n minus 1 with a modulo n operation, we have these funny cosets, but eventually the operation is the same. So we could identify G mod H is going to be identified with simply the integers modulo n, because it's like it has the same number of elements, and the multiplication table, if you will, is the same. But they are not equal, right? I mean, they are different sets. So we will need to make sense of this equality in a precise manner. But for now, you can at least maybe grasp it intuitively that this is another angle to look at the group of integers modulo n. Okay, this will be the end of the material for today. But of course, now is a good time for questions. Hello, are you sure that you don't have any questions?
Is this abelian property necessary?
There is another. So it is sufficient, but not necessary.
Okay.
Right. So in mathematics, I mean, this is how we call. I mean, a condition is sufficient if if it is it gives you what you want, but sufficient and necessary is like if and only if. So the condition that G is abelian is a sufficient condition, but it's not necessary. In fact, even when G is not abelian, then you have a if H satisfy a condition called normal, then the same proposition holds. But for our purposes, we will almost only do quotient groups of abelian groups. So I think it's a good compromise to skip this complication of the non-abelian case and just do it like this.
Okay, thanks.
All right. So I hope you didn't get too bored. I think we covered quite a lot today. Eventually, it may look funny because we come back. It looks like we come back in circles to this integers modulo n. But if you really think of it, we are taking different angles of the same object. And different angles, they add up something to our understanding. So instead of like moving in circles, you can think of we move in kind of a spiral. It means we do progress because we add another angle of another point of view for the object we care about. All right. So see you next week, I hope.
Thank you.
Thank you.
Thanks.
Thank you.
Thanks.